Hello, scholars. Welcome to the Virginia Earth System Science Scholars Program, delivered by the Virginia Space Grant Consortium, NASA, and many industry partners. In this course, we're going to explore the Earth as a system, and we're going to break down the Earth as a system into its subsystems in order to better understand our planet. Much like your body can be broken out into various subsystems as well, the nervous system, the endocrine system, the circulatory system. Likewise, the Earth has systems, and all these systems interact. And those interactions are what we're particularly concerned about in this course. And then beyond that, looking at ways that we study them, particularly through NASA missions. And a lot of these missions, as has been stated before, are missions that you interact with without realizing on a daily basis, because they help deliver weather forecasts, they help deliver climate predictions and an understanding of our current climate. They help deliver a lot of information that people rely on from day to day. They may not get the same press that a Mars mission or a Moon mission get, but they're absolutely critical. NASA's Earth Science program makes the world turn, if you will, in terms of just providing us with the knowledge we need to do our daily things. So let's explore some of these things you might hear about on a daily basis, for which these NASA missions provide information. Just briefly, a couple of them. Things like hurricanes and typhoons. Things like wildfires occurring. Where else are you going to find an image like this of South America looking at current wildfires burning throughout the Amazon rainforest? This image taken during the late summer of, the late northern hemisphere summer of 2019. So at a time when, of course, there were record fires in the Amazon. These are forest fires seen that you can only see from space. These images, and of course, then we can also explore how the biosphere behaves. This video explores just that. You can see increasing CO2 concentrations collected by NASA missions, as well as the vegetation index. In essence, as you see, of course, we're in December. In the northern hemisphere, of course, you can see how things change differently from the southern hemisphere as the year progresses. And this is all because we have satellites in orbit recording this information and providing us with an understanding of how the Earth system works. Just with this image right here, you're looking at interactions between the biosphere, the atmosphere, and the hydrosphere, as well as the geosphere, all making this possible. All right. So as we continue on through our explorations, it's important to point out that the Earth is made up of several subsystems. The lithosphere, or the geosphere, the biosphere, of which we're a part, the cryosphere, the atmosphere, the hydrosphere. Sometimes the cryosphere is not separated out as its own system, just like the anthroposphere is sometimes separated out as its own system, but pulled out of the biosphere. So we can play with this some more. We can even talk about the space environment, or exosphere, if we want to. The bottom line is that all of these individual spheres have particular functions, and they have particular things going on within them that give them their characteristic behavior. So the hydrosphere, for instance, is of course the big thing we think about is a hydrologic cycle, how a drop of water or a water molecule might make its way through the groundwater back to the atmosphere and so forth. But that hydrosphere is dependent upon its behavior. The hydrosphere, the hydrologic cycle, is dependent upon the atmosphere and the biogeochemical cycling that goes on within the atmosphere, which of course are also dependent upon activities within the biosphere and the lithosphere. Ultimately, the gases of the atmosphere come largely from below the lithosphere, from the geosphere. So again, these things are all integrally linked, and you'll note that the existence of these complex systems on Earth makes life possible. To date, there have been no other forms of life found on other planets, which makes Earth very unique. So it's important to understand why. NASA is addressing major Earth system change by looking at a whole wide variety of characteristics of our planet, everything from climate change to natural hazards, some of which are things that humans have no control over. Others are things that humans actually have major contributions toward climate change or air quality, and so forth, sea level rise. Focusing on climate, Earth, looking at Earth as an integrated system through the lens of climate change in particular, we'll look at forcing mechanisms, including solar irradiance and how variations in the sun's energy can affect climate, greenhouse gas emissions, methane and CO2 in particular, and how they affect climate. Aerosols, dust, smoke, and soot all have an effect on climate as well. These are things that force the system one direction or another. Climate feedbacks are features that cause the system to be amplified, or the behavior of the system to be amplified, or the behavior of the system to be not amplified but reduced. So we sometimes refer to positive or negative feedbacks, although the terms positive and negative are somewhat problematic, and saying amplifying feedbacks and reducing feedbacks might be better ways of looking at it. Regardless, clouds, for instance, provide an albedo effect because they're white, and so they will reflect energy back to space, just like ice will, as you see in this image here provided by NASA, where these rays of ice are going to reflect off of the ice back to space, and the ones absorbed by the ocean, because the ocean water essentially behaves as an absorber because of its dark color. That energy is absorbed. Then there's tipping points. Tipping points are a relatively new concept within climate science that looks at these moments, or these moments when the Earth's climate abruptly moves between relatively stable states. You move from a situation of dynamic equilibrium to a disequilibrium to a new dynamic equilibrium. And one of these, there are several important tipping points that we look at: major changes in ocean circulation, major changes in ice loss, and then the rapid release of methane, primarily through the melting of permafrost in polar regions, such as up here in the Brooks Range of Alaska, where you can see these lakes have developed as a result of melting permafrost. The melting permafrost leads to increased microbial activity, which leads to increased methane emissions, which then amplifies climate change, potentially leading to a tipping point. But the melting of the permafrost itself is the tipping point, because you warm the climate to a certain place where the permafrost begins to melt, and then it becomes something that you don't have any control over until a new equilibrium is reached. So these are really, really important to understand. Reaching a tipping point means moving into a completely new regime that we're not used to as a society. Just a brief overview of a couple of missions that are looking at some of these different spheres. We have the GRACE and LANDSAT missions that focus on the Earth's geosphere, looking at gravity anomalies, looking at landscape features in general. We have missions looking at the cryosphere, like IceSat and IceBridge, studying changes in ice mass and ice volume over the Arctic and Greenland and so forth. We have missions that focus on the hydrosphere, such as Aquarius and Jason, that look at sea surface temperature, look at changes in El Nino, La Nina. Atmospheric missions such as ECO and CALIPSO, they're looking at CO2 concentrations, looking at cross sections of the atmosphere, looking at cloud tops and hurricane cross sections and so forth, trying to better understand how temperature and moisture variations lead to changes in weather. And of course, the biosphere. Here we're looking at water stress, and one of these missions here, ECOStress in particular, the coral mission, which looks at coral reefs and so forth. There's a lot of interesting biosphere missions. We looked at a vegetative index a little while ago. Within these modules, as we explore these things, the tools we're going to use are the introductory material, the introductory videos, much like this one, important reference materials, or the quote-unquote textbook, if you will. Then it's going to be your turn to interact by writing an APA paper, by conducting lab activities, and finally demonstrating your knowledge through a brief quiz. Quizzes, of course, are based on the papers and on the lab activities and on the paper material, not on the textbook. Each module will then end with a questionnaire. Well, I hope you have a great time with these VESS modules. I hope you learn a lot. Have fun, communicate with your master teachers, and I will be with you along the way.